Okay, well, welcome back. So, last time we were talking about units. What we're going to do today, to start with, is talk about how to change a quantity from one unit into an equivalent quantity, but with a different unit. This brings us to unit conversions, and then we'll talk about another type of quantity that not only has a magnitude or a size to it, but also has a direction, and these are called vectors. So today we are going to cover unit conversions and vectors. So first, let me ask you, what happens if you take a number and just multiply by 1? So for example, we take a number like 1/2 and we multiply by 1. What do we get? Well, we get a half. We get the same thing back again. Well, when we perform a unit conversion, that is essentially what we do. We multiply a quantity by 1, and we expect to get the same thing back again. But rather than just say 1, let's imagine we multiply by 3/3. Now, what's 3/3? Well, it's the same as 1, but in this case, let's keep the numerator and the denominator separate. So we're going to multiply 1/2 by 3/3. We're going to get 1 times 3, which is 3, over 2 times 3, which is 6. So now, rather than 1/2, we get 3/6. Well, we know 3/6 is equivalent to 1/2, but it's just in a different form. It's equivalent in size, but it's just a different way of writing the same quantity. Well, that's exactly what happens when we convert units. So, let's remember. We know from last time that 1 kilometer is the same as 1,000 meters. In other words, a distance of 1 kilometer is the same as 1,000 meters. Well, what if, what if we divide here and we write, say, we'll divide both sides by 1 kilometer, and we get 1,000 meters divided by 1 kilometer. Now, what does that equal? Well, we've got the same distance in the numerator and the denominator, so we expect that that quantity is equal to 1. Same thing on the top and the bottom, that must equal 1. This is what we call a conversion factor. The values of all conversion factors are equal to 1. Anytime we want to use a conversion factor, we should have an equivalent quantity in the numerator as in the denominator. So if you get the same thing on the top and the bottom, that's going to equal 1. Now, how do we go about using this thing? Well, let's imagine we've got a quantity like, say, 5.73 kilometers. Now, that's a distance. Try and keep in your head about how far this is. If you're familiar with how far kilometers are, think about something that maybe is, say, a little bit between 5 and 6 kilometers away. Or if you're more comfortable with miles, a kilometer is a little bit less than a mile. So think about something that it's kind of on the order of 5 miles away. Less than that, but something on that order. What we're going to do is take this quantity and multiply by that conversion factor. We're going to multiply by 1,000 meters divided by 1 kilometer. We're going to take this quantity and multiply by 1. So what are we going to get? We're going to get something that we would expect to be equivalent to 5.73 kilometers. Well, what do we end up with? Well, let's keep our numerators and denominators separate. We've got kilometers over kilometers. Well, same thing on the top and the bottom. We can treat kilometers like an algebraic quantity, and they cancel out. So we end up with units of meters. And then what's the numerical part? Well, we've got 5.73 times 1,000. Now, if we are strict about our significant figures, you might say, well, 1,000, that's only got 1 sig fig. Does that mean our answer can only have 1 sig fig? Well, last time, remember I said that there are certain quantities that are essentially exact quantities. Now, when we have a conversion between meters and kilometers, 1 kilometer actually is exactly 1,000 meters. It's not approximately, it's only 1,000, it's not only 1,000 to 1 sig fig. 1 kilometer is exactly 1,000 meters by definition. we could think of this as 1.00000, how many zeros we want, kilometers, equal to 1,000.00000, whatever, how many zeros we want, meters, because that is an exact definition. So, although I've only written one sig here, top and bottom, keep in mind that is an exact definition, and so we can assume that has as many sig figs as we want, and so the result is only, the number of sig figs in the result will be determined only by the number of sig figs over here. Remember the rule of sig figs for multiplication. Whatever has the fewest number determines the number of sig figs in the product. Well, we've got how many here? 1, 2, 3. How many here? Well, as many as we want, so our answer will have 3 sig figs. So what is 5.73 times 1,000? 5,730. So what we've done is we've converted 5.73 kilometers into 5,730 meters. Those are different numbers, 5.73, 5,730, but they have different units, so the quantities, the distances, are equivalent. If you think about how far is 5,730 meters, well, you think about how far away that is. If you think about, say, 5,730 yards approximately, well, that's kind of on the order of what we said before, something a little bit less than 5 miles. So, okay, that's looking good. Always try to ask yourself, does this seem like a reasonable result? Does 5.73 kilometers seem like it's the same as 5,730 meters? Well, yeah, I think it is. So, that's good. Very, very good. Okay, now what if we had made a mistake here? What if we had maybe used a different conversion factor? What if we think, okay, yeah, well, we know that 1,000 meters is the same as 1 kilometer. So what if we make our conversion factor 1 kilometer divided by 1,000 meters? That is certainly a good conversion factor. What do we end up with? We multiply, again, assuming we've got as many sig figs as we want. Well, our meters don't cancel out. We divide by 1,000. We get 5.73 times 10 to the minus 3 kilometers squared per meter. There we go. So that's what our conversion is now. Well, now we ask ourselves, is that, whoops, that's no good. Is that the same as that? Well, yeah, as a matter of fact, it is. We certainly have used a perfectly good conversion factor that is the same as that. It's an equivalent quantity. Is it a particular useful quantity? Well, not in the form that we have it there. If we're talking about a distance, if we want to know how far away things are, using quantities of kilometers squared per meter, those aren't particularly useful. So, while this is a true statement, the quantity that we end up with is not really anything that's particularly useful for us. So, we have to go back and think, oh, wait a minute, I used the wrong conversion factor there. To decide which conversion factor to use, ask yourself, okay, I've got kilometers in the numerator with nothing drawn here. Remember, this is the same as like that over 1. So without looking at it like a fraction, anything that doesn't have a numerator, a denominator, you can always just think that that's in the numerator. So we want to get rid of kilometers, so if this is in the top, we know we need to have kilometers in the bottom. If we want to turn it into meters, we know we're going to have to put the meters on the top, in the numerator. And then we ask ourselves, well, what's the conversion between meters and kilometers? Is it 1 to 1,000, 1,000 to 1, whatever? Well, we've got to remember 1 kilometer is 1,000 meters, and then we've got the right conversion factor. So you can always ask yourself, go through the little argument, what do I want to cancel out? What do I want to end up with? And then you can figure out what's the appropriate conversion factor to use. Let's try another one. Let's convert, let's say, 1 mile. So say 1.00 miles, and let's convert this into kilometers. And I'll give us one hint. Let's remember that 1 inch is 2.54 centimeters. So we're going to make this conversion using a number of steps. We'll go from miles to feet, and then feet to inches, and then using this conversion, we'll go from inches to centimeters, then centimeters to meters, and then meters to kilometers. So we'll finally end up with kilometers. So we've got 1 mile, and now we want to get rid of miles, and we're going to convert that to feet. So if miles are on the top, we're going to put miles in the bottom, and feet on the top. And what's the conversion? Well, it turns out that 1 mile is 5,280 feet. You don't need to remember that. Now let's get rid of feet. So feet are on the top, so now we have to put feet on the bottom. We'll convert this to inches, so we'll put inches on the top. And what's the conversion? 12 feet are 1 inch. Oh, no, wait a second, that's not right. Be careful. Remember, 1 foot is 12 inches. So 1 foot, 12 inches. Again, these are definitions, as many sig figs as we want here. Now let's get rid of inches, so we put inches on the bottom, and we're going to convert it to centimeters, so centimeters on the top. What's our conversion here? 1 inch, 2.54 centimeters. Now we'll convert this to meters, so we get rid of centimeters, turn it into meters. Now let's remember what's that conversion. Remember, 1 meter is 100 centimeters, and then get rid of meters, turn it into kilometers, and 1 kilometer is 1,000 meters. There we go. So what do we got? What do we have? Well, we've got miles, cancel miles, miles top, miles on the bottom, feet on the top, feet on the bottom, inches on the top, inches on the bottom, centimeters on the top, centimeters on the bottom, meters on the top, meters on the bottom. We end up with kilometers. So this equals some number of kilometers. And what do we get? 1 times 5,280 times 12 times 2.54 divided by 100 divided by 1,000. And what do we end up with? 1.61. And there we go. And if you think about it, a mile, a little bit more than a kilometer. So 1 mile, 1.61 kilometers. Yep, that sounds about right. That sounds pretty reasonable. Let's try another one. Let's actually use this. Let's remember that 1 mile is 1.61 kilometers. Let's convert a speed. So how fast something goes. So let's say, how fast do you drive on the highway? Well, I don't really want to know how fast you really drive on the highway. Let's imagine that it's a reasonable speed of, let's say, 60 miles an hour. So that would be 60, let's say 60.0, 60 miles per hour. So per means basically miles goes on the top, hours per hour goes on the bottom. So we've got miles per hour. Now let's convert this to another unit for speed. The standard SI unit, which would be, what are the standard SI units for distance? Meters. What are the standard SI units for time? Seconds. So let's convert this to meters per second. Now, how are we going to do that? Well, let's convert miles to kilometers. We know a conversion for miles to kilometers. Let's convert kilometers to meters. For hours, let's convert hours to minutes, and then minutes to seconds. So we'll end up with our speed in minutes per second, meters per second. So we're going to get rid of miles. Miles are on the top, so we have to put miles on the bottom. We want to convert it to kilometers, so we put kilometers on the top. And what's our conversion? 1 mile, 1.00, is 1.61 kilometers. Then let's convert kilometers to meters. Kilometers are on the top, so we put kilometers on the bottom, meters on the top, and we've got 1 kilometer is 1,000 meters. Miles cancel miles, kilometers cancel kilometers, and we've got our distance in meters. Now we need to convert hours to seconds. Now, whoa, wait a second, hours are on the bottom. So where do the hours go in our conversion factor? Well, to cancel them out, if hours are on the bottom here, we need to put hours on the top in the conversion factor. We're going to convert hours to minutes, and what's the conversion? 1 hour is 60 minutes, and then we'll convert minutes to seconds. Now minutes are on the bottom, so we have to put minutes on the top, seconds on the bottom, and what's the conversion? 1 minute, 60 seconds. Again, definition, definition, definition. This is not a definition, and we've got this to 3 sig figs. So, and our original number is 3 sig figs, so our final answer will be with 3 sig figs. And what do we get? Well, let's notice hours cancel hours, minutes cancel minutes, and we end up with units of meters per second. And what do we get? Well, we get 60 times 1.61 times 1,000 divided by 60 divided by 60, and we end up with 26.8 meters per second. Now, does that sound reasonable? Well, let's think about it. Think about driving in a car 60 miles an hour. How fast does a car go past you if it's going 60 miles an hour? Well, how far is 26.8 meters? Well, think about, say, 26.8 yards maybe, or say like 25 yards. How far is that? How far is 25 yards? Well, about, say, a quarter of a football field. A car going a quarter of the way along a football field in 1 second. Yeah, that sounds like pretty fast speed, but that sounds pretty reasonable. So 60 miles per hour, 26.8 meters per second. There we go. So keep in mind that units can be treated just like algebraic quantities. So for example, if you had something like 2x plus 3x, what's 2x plus 3x? It's 5x. Well, in the same way, 2 meters plus 3 meters is 5 meters. So you can add quantities with similar units. You can multiply quantities, even if they have different units. So you could take a quantity like 5x times 3x and get something like 15x squared, because 5 times 3 is 15, x times x is x squared. In the same way that you could take 5 meters times 3 meters is 15 meters squared. So you can treat them just like algebraic quantities. However, you cannot add quantities with different units, so 5 meters plus 3 kilometers is not 8 of something. You have to convert either meters to kilometers or kilometers to meters before you add them together. You can only add quantities if they have the same unit. Okay, now, so far, these quantities that we have been talking about, and with units, other units that we've talked about last time, like mass, or time, or speed, or distance, these are all quantities that we call scalars. Those are quantities which have a magnitude meaning a numerical quantity along with typically a unit. Most scalars will have a magnitude, a size part, and a unit part. Occasionally we will see some quantities that do not have units, and we'll point those out as we get to them. There are quantities that have something in addition to the magnitude part, and that is a direction, quantities that have a direction associated with them. For example, if I were to say that I'm going to move 1 meter, do you know what I'm going to do? Well, not necessarily, because I could move to my left 1 meter, I could move to my right 1 meter, I could jump up in the air 1 meter. If I were to say I was going to move down 1 meter, that would be very hard. I would have to dig a hole through the floor or something like that. So, in that case, knowing the direction is very important, because they would all be very, very different kinds of things. Well, quantities that have not only a size part, which is the scalar part or the magnitude part, but a direction are what we call vectors. So vectors are quantities that have a magnitude, which is the size part of the vector, and a direction. So magnitude and direction. Now in the textbook, when vectors are indicated, typically they're written in a bold font, so very bold. That's kind of hard for me to draw. When they want to talk about the magnitude of the vector, they write it in italics, and so I can't really write italics very well either. So bold would mean a vector, italics is the magnitude of that vector. On the board, and typically in class, when I want to distinguish between those, I'll write a vector with a little arrow or a vector sign on top. So anytime we've got a vector quantity, I'll put an arrow on top. If I want to indicate just the size of that vector or the magnitude of that vector, I'll just write that quantity, but without the vector sign on top. So vector signs means, or an arrow means it's a vector. No vector sign, it's a scalar. All right. Now, to describe the direction of a particular vector, typically we will use a coordinate system. Now, if you're talking about moving around in the city or something like that, you might say you're going to go so many miles to the north, or so many miles to the east, or northeast, or something like that. So the coordinate system that's typically used when you're talking about moving around on the surface of the Earth, we talk about east and north. However, we're going to be a little bit more general than that. Rather than north and east, we are going to talk about x and y. So x and y. And we will talk about vectors in their relationship to our x and y coordinate. And we can define our x and y coordinates any way we want. Typically, we'll usually think of x as being horizontal and positive increasing to the right, y as being vertical and typically increasing upwards. That's not necessarily always the case, but for the most part, that's what we'll use. And then when we want to describe a vector, we will describe it relative to those x and y coordinates. If we want to talk about back in this direction, we'll emphasize this as the negative x coordinate, or down this way would be the negative y coordinate. Okay, so let's just say we're going to go for a walk. We're going to describe our walk relative to our x and y coordinates. Let's say we go for a walk that is 20 meters long. We walk for 20 meters. That is at an angle of 25 degrees up from the x-axis. So up from the x-axis, here's the x-axis, up from the x-axis, 25 degrees. So there's our vector. Let's assume that that is then 25 degrees, and we walk for 20 meters. So we can represent our motion, our walk, you might say, to look like an arrow. And this is going to be something that we're going to use a lot. We're going to represent vectors with an arrow. An arrow has a particular length from one end to the other. That's the magnitude, the length or magnitude of the vector. And then we can have that vector point in any direction we want. We could have it come out of the board or into the board or any direction we want. So we can represent the direction of the vector physically like an arrow. And very often we will represent those vectors with arrows and kind of very physically think of them as an arrow type thing. Now, one thing that is important is that it does not matter where we draw that arrow. As long as it has the same length and the same direction, it will be the same vector. So, for example, we might imagine these two arrows. They have the same length and the same direction, so these are the same vector. Same vector. Same vector, same vector, same vector. These are not the same vector. Although they have the same length, the same magnitude, they have a different direction. So they're not the same vector. As long as they are pointing in the same direction, in other words, as long as they're parallel to each other, we will assume, we will take them to be the same vector. They don't have to be exactly on top of each other to be the same vector. Okay, so this vector, we could have just as easily drawn it up here, or down here, or over here, or out here. As long as it's pointing in the same direction, with the same magnitude, it's the same vector. But sometimes it's just easiest to draw it starting from the origin of our coordinate system and going up in some direction, but it doesn't have to be. All right. Now, when we talk about going for a walk or moving from one point to another, this type of vector is called a displacement vector. Displacement vector just means a motion vector from one point to another, going from an initial point to a final point. That's our displacement vector. Okay, now, a very, very important quantity or a very important process that we're going to have to deal with is how to combine vectors. the simplest way to think about this is to go back to our idea of displacement vectors and ask, how do you combine displacement vectors? And that's the same way as you would combine any other type of vector, no matter what kind of vector it is. All right, so let's think about going for a walk, and our walk has two parts. In other words, we're going to go through two different displacements.